Okay, so my brother was wondering why the derivative of x to the n is equal to nx to the n minus 1. So I'm going to make a quick video to prove this using just the definition of a derivative, which is the limit as x approaches a of f of x minus f of a divided by x minus a. I prefer for this to use the alternate definition of setting h equal to x minus a, and then taking the limit as h approaches 0 of f of x plus h minus f of x divided by h. So for x to the n, we have x minus h to the n minus x to the n divided by h. Of course, it's the limit. Okay, so the first thing we are going to do is kind of just take this apart here. We are going to use a binomial expansion for x minus h to the n, which gives us the sum from I equals 0 to n of n choose I, x sub I, h sub n minus I. Okay, minus x to the n divided by h. So the goal is going to be to cancel this h out of the denominator, of course. That's always the strategy to use when you are using the definition to prove something. So in this case, we need to get rid of our x to the n, which we know is, of course, the last term of the binomial expansion. But we also need to pull out our nx to the n minus 1 term, which is, of course, our x to the n minus 1 is going to be our second to last term. So we're just going to set this equal to I equals 0 to the n minus 2 term of n choose I, x sub I, h to the n minus I, and this is going to be plus h n x to the n minus 1 plus x to the n. This is just this guy. So we put that together down here, and we have the limit as h approaches 0 of, let's see, the sum from I equals 0 to n choose I, x sub I, and then we're going to have h to the n, whoops, this is n minus 2, h to the n minus 1 minus I, since we canceled out the h. And then our x to the n is going to cancel with this x to the n, and then this h is going to cross out. So we have plus nx to the n minus 1, and then we just take the limit as h approaches 0, and that is going to tend towards, of course, nx to the n minus 1.